Hi guys, Sajjad again with a new video. In this video I am going to design a concrete building based on this reference, seismic and wind design of concrete buildings based on IBC 2000, ASC 798 and ACI 31899. And I will take this example. In this example, basically this building is located in Miami. Concrete properties are F-C is 4000 psi and Fy is 60,000 psi, normal weight concrete. In plan, this building has dimensions like this. There are 7 bays in X direction and they are equally spaced, 26 feet, 26 feet, 26 feet, and in Z direction or in north-south direction the bays are 22 feet wide. This building has 12 stories. The first story is 16 feet high and all the remaining stories, they are 12 feet high. As per this example, the service live load at roof is 20 pound per square foot. At floor it is 50 pound per square foot. Superimposed dead load is on the roof 10 pound per square foot plus another 200 kips for penthouse. Floor load is 30 pound per square foot. The seismic data is SS is 0.065 G, S1 is 0.024 G. Site classification is D, that means this is a stiff soil profile as per IBC table 16.15-1.1, and the occupancy is 1. Similarly, the wind data is given as 145 mile per hour is the speed, exposure condition is B, and occupancy is 1. The member dimensions are as follows. The slab is 8 inch thick, beams are 24 inch by 24 inch, columns are 28 inch by 28 inch, the wall thickness is 12 inch. Basically there are 2 shear walls, one along grade 2 and one along grade 7 in north-south direction. So let us model this in STAAD. Start a new project. It should be space, unit should be foot and kip, and let us name it 12 story building, and let me select the drive seismic design of a 12-story building. Next, finish. Let me close this. Let me use the section wizard. Let's see the unit first. The unit are in feet. Okay, it should be a frame model. It should be bay frame. Okay, length, there are 26 into 7 means 26 feet multiplied by 7 is 182. 182. There are 7 bays and sorry, it should be 182, and in this direction it should be 66 66 3. The height is 11 into 12 plus 16, that means 148 feet. There are 12 bays. Now let us take it 144 and 12 bays. Later on we will change. That will be easy. So it will look like this. Let us merge the model with the STAAD. Here it is merged. We know that the ground floor story has a height of 16 feet. So let us move all the joints in y direction by -4 feet. Okay. Let's see the origin. Okay, let's move the origin also. -4 feet. Okay, fine. Now we can assign, since all these nodes are selected, we can assign support conditions. Let us assign fixed support to all these. Let us save this model. Now let us assign the properties. We know that all the beams are 24 inch by 24 inch. Let us select the beams which are parallel to x direction, beams which are parallel to z direction. Let us assign member properties. It is rectangle. 24 means 2 feet by 2 feet. Assign. Okay. I don't want to see the sections. Close. Let me change the foot into inches. Let us assign the member properties for column. Select all beams which are parallel to y. All columns were 28 inch by 28 inch. We know that there were two shear walls, one in this direction on this grid, another one is on this grid. Let us model the plates. So it is beam number, joint number 314. Let us select YZ plane in direction of node number 314. Let us add one more beam over here so that it will be easy to model the elements. Let us select the elements. We know these walls are 12 inch thick. Let us assign to the plates. Okay. Now we can generate this. Let us generate transitional repeat in y direction at 12 feet interval. There should be 10 and more. Okay, let us select all plates. So here are the plates, and then we can translate this in x direction at a distance of 130 feet. So let us translate in x direction at 130 feet. Okay, let's see, select all plates. Fine. Now we should model the slabs also. Let us model the slab. Let us select the first floor. So let us select the first floor and define the elements. I don't want to see this, it's confusing. Let us define the first element. Select all plates. No, something wrong. Sorry. We have to define the plates. Select all plates. This slab is 8-inch thick concrete slab. Let us assign the properties. Let's change the unit. Plate thickness 8 inches. Assign. Okay. Close. Let us generate these plates in x direction. Translational repeat in x direction. There will be 6 at 26 feet. Sorry. Okay, let's see, select all plates and let us translate in z direction also. Geometry, translation repeat in z direction. It will be negative 22 2 times. Okay, so let's see, select all plates. So here are the plates, these are the slabs, and now we have to repeat them for another 11 stories. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So geometry, translational repeat in y direction every 12 feet. One more. Okay, there are 11 repeat. So let's select all plates. So the model is complete. To see the properties, so we have defined the beams, we have defined the columns, we have defined the shear wall, we have defined the plates. Let us check if there are any duplicate member. Yes, there is. So okay, I have to keep the original one because so that was a mistake. It is rectified now. So far we have completed our model. Now we have to define the loads. Let us first define the seismic load. If you remember, the parameters for the seismic load given was that SS will be 0.065, S1 will be 0.024, and this we have to follow IBC 2000. Let us see if we select IBC 2000. When we select IBC 2000, these parameters are different. Even IBC 2003, the same parameters. If we select IBC 2006, which is based on ASC 705, then these parameters are SS and S1, which are correct. Here the data given was 33122, that was the zip code. Let us input the zip code 33122. Then the longitude and latitudes are given, and the SS values are and SN values, S1 values are a little bit different. So let us not use the zip code, neither the longitude or latitude values. Let us delete these values and let us define SS value as per the given data. So the value of SS given was 0.065. Value of S1 given was 0.024. TL is the long time period, which is 12 seconds by default, correct. We should not change this one. Importance factor is 1, that is correct, no problem. As per IBC table, FA comes out to be 1.6, FV comes out to be 2.4. Now the important thing is that in X direction the shear wall is not going to act, but in Z direction the shear wall is going to act. So for ordinary, now first we will be defining this load case or design parameters, seismic design parameters in X direction. So in this case, in X direction, the value of R will be 3, and in Z direction the value of R will be 7 because there is the shear wall. Site loss of course D, that is 4, and as per the parameters given, the time period has already been calculated, and this calculation I can show you. In north-south direction, which is our x direction, our z direction, the time period is 1.2, and in x direction, which is east-west direction, the time period is 1.27 seconds. So let us input these values. In x direction, the time period is 0.85. In x direction, east-west, the time period is 1.27, and in z direction the time period is 0.85 as calculated. Since the time period has already been given, no need to give ct and x values. Let us add. Now the surf weight is 1, we will add. And if you remember the superimposed dead load, the floor loads, superimposed dead load on the roof was 10 pound per square foot, and on the other floors the load was 30 pound per square foot. So let us assign 30 pound means 0.030, .03 kip per foot square. The Y range is from 0 feet up to, it will be 10 multiplied by 12 plus 16, 136, say 140. Let us add these values. Okay. We have to add more load, that is at the roof 0.01 kip per square foot, and this will be at a height of 148, let us see, 147 to 149. Add. Then there were 200 kip for the penthouse, which will be on the rooftop. So let us assign the penthouse load also at the rooftop. Let us distribute that 200 load on these 8 nodes. So let us add joint nodes, 25 kip, and let us add to these nodes, all 8 nodes. Let us assign to the selected nodes. Yes. Save. So we have defined the seismic load, the parameters for the seismic load, and now let us define the load. Add first load case is the seismic, load case 1 is the earthquake load in X. Add, let's add seismic load in X direction, factor 1, add, and let us add for load case 2 seismic. This is also earthquake load in Z direction, let us assign seismic load in direction Z1, add, okay, fine. Let us save the file, then we should say perform analysis. Okay, save this file. Let us have an initial run and let's see what the results are. Oh, there is something wrong. Oh, member 109. What is member 109? Select by missing properties. Oh, that beam was missed. Okay, properties, select okay. Now let us save the file. Let us see whether we have added this beam over here or not. XY in YZ direction. No, so let us add this beam also. Fine, let's save the file. Close. Let's analyze and see. Okay, let's see the output. Actually, I was very much interested in the definition of this value, which is called Cx, that is the coefficient. Here the coefficient comes out to be 0.01. Let us see what is there in the example. If you see this paragraph 2.2.2 seismic load analysis, it is said that the SS value is less than 0.015 G and S1 is less than 0.04 G. No need to comply with the requirements of the 1660.4 paragraph that requires the pseudo-static analysis, and they say the minimum lateral force Fx applied simultaneously on the floor, it should be 0.01 times Wx. That means the base shear is nothing but 0.01 times the weight. That means in this particular case where the building falls under SDC A, that means the seismic design category A. The base shear is very simple and that should be 0.01, and what STAAD has given us the same thing. .01 multiplied by the total dead weight, which is 329. Here in 326, slight difference, that's okay. Let us see how much is the base shear calculated. As per the estimate, the base shear calculated is 291, which is very close to the STAAD value. So this is an approximate calculation. That means the STAAD has given us a perfect calculation for the base shear, and of course the lateral distribution will be as per this one. There's no doubt in it. That means so far we can say that safely we can use the seismic load generator of STAAD as per IBC 2006 or ASC 705. Hopefully you will like this video. I'll stop now for this load case, for the seismic load case definition now. In the next session, what I will do, I will generate the wind load factor. So for that time being, goodbye. Thanks.